What's up guys, it's Izzyhedron, and today I want to showcase a new technique I found using Desmos 3D to obtain cross-sections of 4D polytopes. I'm particularly excited about it because you can basically freeload off of Desmos 3D's implicit equation solver to slice any shape that can be defined using a condition. But first, before we think about taking cross-sections of 4D solids, let's first consider a method to display a cube in any orientation. Here we have the 3D space defined by x0, y0, and z0, and here is a cube we want Desmos to display. Now imagine we have a function that returns a value below 1 whenever a specified point is inside the cube. Then on Desmos we can graph this cube as the region in which this inequality holds. As it turns out, there's a nice expression for f. But this only allows us to display a cube in one orientation. We want any orientation. To remedy this, let's create a transformation that performs a rotation about the origin to get from x0, y0, z0 to xyz. The exact details of this rotation function are not very relevant. In this new coordinate system, let's display the region in which f of x0, y0, z0 is lesser than equal to 1. If we define an inverse to the rotation function, the above expression can be defined in terms of xyz as follows. Sure enough, this equality will allow us to display a cube that's rotated about the origin. We can confirm this on Desmos and adjust the rotation parameters as we see fit. We can repeat this entire procedure for 4 dimensions. This hypercube is the region where f of x0, y0, z0, w0 is lesser than equal to 1. This function is defined very similarly to our 3D equivalent. Now let's imagine a function that rotates x0, y0, z0, w0 about the origin to obtain x, y, z, w. We can display our rotated hypercube very similarly to last time, as the region in which f of x0, y0, z0, w0 is lesser than equal to 1. Unfortunately, this equation cannot similarly be easily visualized in Desmos. Now here's the trick to displaying a cross-section. We can allow x, y, and z to change in our 3D viewport with respect to position, but fix the w value of every point. Changing the w value will allow us to see different cross-sections, like we're scanning through an MRI machine. Here's another way to visualize these cross-sections. If a 4-dimensional extraterrestrial was going through our universe, we would see these cross-sections. We would not be able to see the entire 4D picture. But enough talk. Now let's see what it looks like in practice. When the rotation parameters are all equal to 0, the hypercube will just look like a cube blinking in and out of existence. We can get more interesting behavior when the rotation parameters are not all equal to 0, akin to saying we're rotating the shape before taking cross-sections. We can get even more interesting behavior when we set the rotation parameters to values that preserve different symmetries of the hypercube. This one's probably my favorite. It shows a tetrahedron morphing into an octahedron, which then morphs into an opposite tetrahedron. Anyway, that's about it for the hypercube. But if we're willing to change our function describing the shape, there's a whole host of 3D shapes we can make 4D and then take cross-sections out of. There are relatively simple inequalities that can help us visualize a sphere, an octahedron, a cylinder, and a torus. Now let's make them 4D by extrapolating what their formulas might look like with the w variable. Here we can turn a 3D sphere into a 4D sphere, we can turn this cube into a hypercube, we can turn this octahedron into a hyperoctahedron. For the cylinder, there are 2 equally valid ways to add a w, yielding 2 distinct shapes, colloquially known as the cubinder and sphereinder respectively, and the same goes for the torus, yielding a spherotorus and a torosphere. Now let's take cross-sections of them. The 4D sphere behaves in a way that you might expect if you stare at the equation for long enough. The same goes for the hyperoctahedron. The cubinder blinks in and out of existence like we saw for the hypercube, and the sphereinder grows and shrinks like the cross-sections of the hypersphere. I think the tori are where things begin to get pretty interesting. Now let's try rotating the 4D shapes before taking cross-sections. Okay, so now I want to tell you about this cool thing called the 24 cell. So there are 5 platonic solids in 3 dimensions, but there's actually 6 in 4D, and the one that doesn't correspond to a 3D platonic solid is the 24 cell. It's self-dual just like the tetrahedron, and it has no analogs in higher or lower dimensions. Anyway, if you couldn't already tell, I think it's the coolest thing ever, and its 3D equivalent is the rhombic dodecahedron. So in order to take cross-sections of the 24 cell, let's first figure out a good inequality that will give us the rhombic dodecahedron. My first very lazy idea was to imagine the rhombic dodecahedron as some sort of combination of a cube and octahedron, so I could linearly interpolate the functions that describe a cube and octahedron and see if at any point I get a rhombic dodecahedron. Unsurprisingly, it did not work. My next course of action was to observe that the rhombic dodecahedron is just a cube with a bunch of pyramids on it. As it turns out, there's a way to generate these pyramids for each axis. Putting them together gives us a rhombic dodecahedron. We can generalize this to 4D to get these 4 inequalities that together compose a 24 cell. This piecewise approach resulted in annoying seams between segments, but I found these could be mitigated by adjusting the threshold f of xyzw equals 1 to somewhere around 1.05. And with that, although there's a bit of lag, we can slice the 24 cell. It's honestly not what I expected, but it looks pretty cool. An alternate orientation yields an octahedron that grows into a cube octahedron. Anyway, I thought I'd end the video with some cross-sections of shapes we've already looked at as well as some new shapes. I hope you enjoy.